Well, hello, everybody. Nice to see you. My name is Eugenia Etkina. I'm from Rutgers University. And the title of my short presentation today is When Learning Physics Mirrors Doing Physics. Well, let's start with a picture that you probably all saw. You know, a child eating dirt. Why would children eat dirt? We can approach this question from a physics point of view, and it would look like something like this. So dirt, looks like chocolate. Well, then if it is chocolate, when I eat it, it will taste like chocolate. So this is our testing experiment. If you look at this quick process, you see that that's exactly what physicists do when they discover new ideas. But there's more to this, simple picture and the funny process that I described. If you look at children trying to master tricks on skateboards or bicycles or figure out computer games, you will see amazing skills that they demonstrate. They try and fail again and again and again. They test the ideas experimentally. They persevere, they work together. And they're doing all this because they want to do it. They're motivated. And what we say in education, they have the need to know. So why don't they do it in our classrooms? Well, I don't want to be really controversial, but I will be. I think that the problem is that traditional and even reform teaching goes against much of what we are good at and much of what we know helps people learn. What do I mean? Well, the answers come before questions. We tell students something that they have no need to know yet. Grades, we give them grades for their work. They don't have an opportunity to improve like the kids who are doing tricks on their skateboards or bicycles. So they don't have an opportunity to try without being afraid to fail. We preset the pace of the curriculum. So if you're learning at a different pace, you're punished for it. If the class being graded on a curve, then you're also punished for collaborating with your peers. And if you have traditional problems, and I mean the problems that have one right answer, numerical answer on the multiple choice test, then you punish those who need reasoning tools other than mathematics, and in our physics case is algebra or calculus. And what's important that for women, all these issues are exacerbated due to their tendency to blame themselves and often having an imposter syndrome. So if I feel that I don't belong to this environment, then I will not collaborate with other people, so I will not be a part of a learning community. Well, there's more to it. We teach physics as religion. What do I mean? We tell the students the ultimate truths, and then we'll let them practice it. We tell them this is Newton's second law. This experiment can be explained in this and that way. And then now you go and you apply what I just told you. But we do physics as science. So there is a huge disconnect between the social aspect of how people learn and what actually physics is about when we teach it. So what is the solution? Let me show you an example. We could start with something that everyone experiences, but rarely questions. So, for example, you all observed this, right? Everybody popped a balloon in their lives. The question is, where does this loud sound come from? So, get students in groups. They propose explanations that we call crazy ideas. They discuss stuff with each other and say, okay, maybe the sound is made by air that is coming out of the balloon. How can we test it? Again, the students work in groups and come up usually with an experiment. Well, let's fill the balloon with something other than air. Let's fill it with water. If the air is responsible, then the water will not make a loud sound. And we do it. Well, there is some sound, but not nearly as loud as when the balloon is filled with air. So did we prove that the air was responsible for the loud sound? Well, in physics and in science, one experiment that has the outcome that matches the prediction is not enough to prove that the hypothesis on which the prediction was made is correct. So let's do another experiment. So how else can we test the air? They say, okay, if we just want to test the air, we need to remove the rubber from the picture, right? Because the rubber was also a part of the balloon. So how can we do it? Well, let's put air in something that is not rubber. For example, a shopping bag made of plastic, and then poke it. If air is responsible, then we will hear a loud sound. So let's do the experiment. Oops, that's still the water experiment. Now we are going to do, oops, no sound at all. So now did we disprove the air that we just confirmed with the water? So it looks like that the problem is more complicated. The students go back to their groups and they come up with a new idea. Maybe it is not the air, but the rubber. So then let's just have the rubber and pop it with a needle. If it is just the rubber, it should make the loud sound. Here we go. Just the rubber. Well, there is some sound, but not nearly as loud as when we poke the balloon. So it looks like the air is important, but we don't know how. And the rubber is important, but maybe it is how they work together. So what is different from the balloon when the balloon pops compared to when the shopping bag was popped? The balloon rips apart. So maybe it's how fast the rubber is breaking and letting the air out that is responsible for the sound. How can we test that? The students go back into their groups and they work together and they come up with an idea that we need to take the shopping bag, but in plastic bag, but instead of poking it with a needle, we need to make the air come out fast. So we need to kind of bang it together. So let's do it. So we see a much louder sound. So now we can go and ask more questions. Why did we need to do it? What makes the sound? And the whole unit on the sound is started. And you might say, well, that was easy. What about a more difficult idea? Can we use the same approach that we did for the sound of the ripped balloon? So here is a more difficult idea. So imagine that your students learn kinetic molecular theory. They know that air consists of molecules, that they also learn electricity, magnetism, and electromagnetic induction. They know about conductors and dielectrics. They're familiar with ionization of air. And they also learn wave optics, and they know the electromagnetic wave model of light. So they're now convinced that light phenomena can be explained with an electromagnetic wave model of light. Here, and so for them, light behaves as a wave of alternating electric and magnetic fields. So now they observe the following experiment. So they're familiar with an electroscope. We rub a plastic rod with a felt, and we know it's charged negatively. We touch the electroscope and we see the deflection. So now electroscope, the top of the electroscope, remember it's made of zinc, is charged negatively, as well as the metal holder and the needle. So we shine the visible light, nothing happens. Now we shine UV light, and the electroscope discharges. So the students get into groups and they need to figure out what is the mechanism behind the discharging of the electroscope. And before they learn that electroscope does not discharge by itself because the air is an insulator. So the students get together and usually come up with an idea that UV light ionizes the air that becomes a conductor. And because there are ions and free electrons in the air, and the electroscope is charged negatively, the positive ions surround the electroscope and discharge it. So the air, the ionization of air, is responsible. How can we test this idea? Well, if this idea is correct, then the UV light should discharge a positively charged electroscope. Let's check it out. So now we take a glass rod, and we know that rubbing it with silk causes it to be charged positively. We charge the electroscope positively and shine visible light. We don't expect anything to happen. According to our idea, visible light does not ionize air. And then we take UV light and we shine, and nothing happens. So UV light does not discharge a positively charged electroscope. So we reject our idea, our crazy idea of ionizing air as the reason for the discharge of the negatively charged electroscope. What else can it be? Well, we start thinking, the students start thinking that maybe it wasn't a good explanation, but maybe there's another explanation. Maybe UV light kicks electrons out of the zinc plate. How does it? We can actually hypothesize, because it's made of oscillating electric and magnetic fields, and maybe the electric field transfers energy to the electrons and they leave. Great. A really possible idea. If this idea is correct and we shine light on the neutral electroscope, it should charge positively, right? So let's check it out. So remember, we need the zinc plate to have the same material. We shine UV light, nothing happens. So does it mean that the UV light does not charge a neutral electroscope because our idea is incorrect, or we forgot about something? So let's think about, why didn't the electroscope get charged? So what do we know about the structure of metals? Inside there's a crystal lattice and free electrons. So maybe the UV light did kick out these some of the free electrons, but once the electrons leave the electroscope, it becomes positively charged and attracts the electrons back. So that's why it didn't get charged. So it's not that our main hypothesis or idea was not incorrect. It's that we overlooked the assumption of how to charge an electroscope and what is happening when it gets charged. So if this is correct, then we need to somehow, if we are shining UV light on a neutral electroscope, we need to pull away those electrons that came up. So how can we do it? We need to bring some positively charged object close to our neutral electroscope while it is being illuminated by UV light. So if all our ideas are correct, then in this case, the neutral electroscope should be charged positively after shining UV light on it. Okay, let's check it out. And the students, of course, get nervous because they propose the experiment and they know what should happen if the ideas are correct. And now they're not testing the ideas, they're validating the assumption of why the previous experiment did not work. So we take an electroscope and charge it positively. This will be something that will pull the electrons off the electrons that came out of our neutral electroscope on which the UV light is shining. So see the zinc plate, neutral electroscope, and we have this mesh so you can see what's going on. So now see that positively charged electroscope, we're shining UV light on a neutral electroscope, and it's showing some charge. Whoa. So before the UV light was shining, this electroscope was showing no charge. And now the charge on the positively charged electroscope decreased, and our neutral electroscope acquired a charge. But according to all our reasoning, both should be still charged positively. So how can we test that? Well, what we can do is bring a positively charged rod close to both of them. And so if they're both charged positively, bringing a positively charged rod will show the increase of the charge, even without touching. So let's see if this actually happens. So these are our electroscopes. We separate them, they're charged. And so that's a positively charged object is bringing, oh, the charge increases as we predicted. And here, yes, the charge increases. So the reading increases, the charge doesn't change. So what does that mean? It means that the neutral electroscope got charged by UV light shining on it. And it means that UV light really can kick electrons out of the electroscope. So how does it do it? And why it is important? That's a great question. And that's how we start the exploration of the photoelectric effect. And what I showed you is the process that we follow when we use the investigative science learning environment approach to learning and teaching physics. Every difficult idea that students need to learn or construct in a physics course starts with observational experiments, when they observe something without making any predictions, with an open mind. They identify patterns in these observations and come up with explanations. We call them crazy ideas to reduce the weight of rightness. They don't need to be right at all. In fact, it's better if they turned out to be rejected, because rejection is easier than proof. Every explanation needs to be tested. So they need to design a testing experiment and make prediction, not based on their intuition. We're not testing their intuition, but on the explanation or a model that they just proposed. And if the outcome does not agree with the prediction based on this explanation, it doesn't mean the prediction was wrong. It means that we need to reflect and rethink. We either propose a different explanation, like we did. Instead of the air, we proposed electrons leaving the metal, or we need to check assumptions, just as we did when we saw that the neutral electroscope did not discharge. Or sometimes we say that we didn't have enough data to even propose a model, so we need to conduct more observational experiments. But when the outcome match, we need to conduct more testing experiments, and that's what we did when, remember, we said the air is responsible. We put the water in, it went like we predicted, and we conducted another experiment, and it didn't go the way we predicted. So we need to do more than one testing experiment. And then once we say, okay, we cannot reject this idea, we proceed to application experiments. But there's more to this approach. I don't have time to talk about it today, but when you ask your questions, you're welcome to do it. We have an array of multiple representations that are our reasoning tools, like hammers and saws when we build a house. We have motion diagrams, force diagrams, energy bar charts as tools helping the transition from the language to the algebra or calculus. And what is important, that students work in groups, in small groups, and the groups share their ideas through the whiteboards. They form a learning community, and the students have opportunities to improve their work without punishment. You saw this natural improvement when students are constructing new ideas, but even when they write a lab report, if they do a quiz or homework, they can always resubmit, and whatever grade they receive, this is their final grade, not reduced because it's a second or a third attempt. So the IEL approach is an example of an intentional approach to curriculum design. What does it mean? Intentionality means that the product of knowledge cannot and should not be separated from the means by which it came to be known. And what does that mean? It means that when we're setting up our classroom, we need to think, what does the setup tell the students about what's going on? For example, we want them to read the textbook before they come to class. This is a very strong message that their knowledge of physics will come from the textbook. And what we want our students to, so what intentionalities we want to communicate to our students is one, about what and how students learn. And the second one is how students feel about learning physics. So the first intentionality is based on the idea that if we want students to learn the process of physics, they have to be engaged in this process, right? And the second is that if a person is unhappy doing something, they will not be motivated to do it. So that means that students learn physics by practicing it, and students develop confidence and growth mindset. So where did these intentionalities come from? The first one comes from the history and philosophy of science, observation of physicists, and brain studies. And the second comes from the studies of learning communities, motivation, confidence, and cognitive development. So I'll give you an example of a history of physics that motivates the approach that we just did. Photoelectric effect. You probably remember that it started by an accidental observation of Henry Hertz, who saw that when you have two charged spheres, the spark between them jumps easier if the sunlight is shining on it. If you enclose this in a glass container, then you need the charge much higher for the spark to occur. He said, well, that's an interesting observation, but I have no time to investigate it. So Wilhelm Haurachs conducted experiments similar to what we did with an electroscope and figured out that the sunlight contains a component of UV light that leads to the discharge of a negatively charged electroscope. But he did not investigate the quantitative aspect, so he couldn't make any mathematical models. So this was done by Alexander Steletov in Russia and Philip Leonard in Germany. So they conducted quantitative observational experiments and tried to come up with explanations using the electromagnetic wave model of light. And of course, as we know, some of the observations could not be explained by electromagnetic wave model of light. So Albert Einstein comes and says, well, let's take Planck's assumption that light is emitted by portions and extend it to the hypothesis that light is absorbed by portions or quanta. And this hypothesis, this explanation, explained all the observations that were conducted before. So Robert Millikan said, well, this cannot be true, and I'm going to show that you're wrong. I'm going to disprove your hypothesis. And so he worked many years trying to disprove Einstein's idea because he knew what it predicts for a certain experiment. And unfortunately, he could not reject it. So he got a Nobel Prize for the failure to reject Einstein's idea. And later, the first multiplier tubes were built based on the idea of the explanation of the photoelectric effect. And now there's probably no device in the world that doesn't use it. So we can put these people on our aisle progression of logical ideas. We also conducted experiments with physicists in real time when they were solving problems that were new to them. It turns out that they follow pretty much the same process. Of course, it's not a linear process at all, as we discussed, but the elements of reasoning and the connections between them, they remain. Cognitive science tells us a few very important things. First, learning is a social process. And that's why IEL students work in groups, coming up with ideas, testing them, and solving problems. Fixed or growth mindset, you probably heard these words, determine how a person will learn and what choices they will make in the process of learning. And So we give our students an opportunity to improve their work, and we encourage them to do it. And that shows them that what they learn today is not the end, that they can do better than that. So it helps develop the growth mindset instead of, well, today you didn't learn this, you're getting a C and we're moving on. But this resubmission, this improvement of their work and our encouragement for them to improve their work is really important because it develops perseverance. And perseverance, as we know, is one of the major predictors of success in life. If we think about students taking our physics courses, very few of them will become professional physicists or doing research in physics. They might only take this one physics course. So what will they take from this physics course? Will they feel that it's connected to real life? Will they feel that they belong? Will they feel that they're good at it? Or they will feel like most people who you meet and they ask you, what do you do? And you say, I teach physics. They say, you must be smart. Why would they say it? Well, because this is the perception of physics as being very difficult and only for brilliant people. So I hope that our approach helps everyone to be welcome and successful in learning physics. A lot of people work on the development of our materials. We have a whole book that describes it. It's called Investigative Science Learning Environment, when learning physics mirrors doing physics, exactly like the title of my short presentation. We also have an algebra-based physics textbook that is used in colleges, universities, AP physics courses in high schools, and any basically high school physics course that can be used. Comes with the active learning guide with activities and the instructor guide, lots of free videos. We also have a website that allows you to download the labs based on this approach and use formative self-assessment rubrics. We have another website with lots of videos and questions that all follow this philosophical approach. We have specific materials completely free for middle school and high school physics. And we have games that allow you to learn some of the concepts of physics using this approach in a gaming environment. Well, thank you, and prepare your questions. I will be happy to answer them next time we meet. Thank you.
In the chat. Our guest today is Eugenia Etkina, who is a distinguished professor at Rutgers University in the Graduate School of Education, but she also has an affiliation with the physics department there. Eugenia was trained in physics education in the former Soviet Union, and has been, I think, at the forefront of improving physics education in this country. In fact, she is a 2014 recipient of the Millikan Medal of the American Association of Physics Teachers. And I don't want to take too much time because I think I am more interested in hearing from Eugenia than hearing myself speak here. I was so excited seeing your talk, Eugenia. So thank you, first of all, for joining us on a Saturday, and thank you for an absolutely phenomenal talk. I mean, it sort of resonated with me in many ways, and the system you designed, this investigative science learning environment, which is really the cornerstone of your talk, when learning physics mirrors doing physics, resonates with me very strongly. And in a sense, it's sort of the difference between inductive and deductive reasoning. I think one could say that lies at the heart of your thesis. And as you know, I've always promoted going from the specific to the general rather than from the general to the specific, because what is important is that we teach physics or science in general. I don't know why I'm saying physics, because this is really much more general than physics, as a way of thinking rather than a collection of facts or skills. So one question I have, and I know you probably get it many times, I get a similar question, but I would love to hear your feedback, is going through the scientific process, and you don't need to convince me that that's the better thing to do, obvious, because that's why I became a scientist, doesn't permit you to get as deep into, or maybe as broad, I should say, you can get very deep, as broad into the content as the normal, just give the facts, present the statements of science approach. So where do you see the right balance should be? Should we do very little content and focus completely on discovery, or should we still try in an introductory course, either at the high school level or an intro physics course at the college level? Should we try to still cover the standard curriculum, which is really close to 3 centuries of physics? So where's the ideal balance in your mind? Or is there a way to do both?
That's a good question. Well, I think the most important question is, what do we want to accomplish? Like, what is the goal of students learning introductory physics? And you can ask this question about any level of physics, but I'll be talking about introductory physics because this is the closest to the physics teachers. So think about it. How many of your students will become professional physicists? Maybe, 1 or 2 a year in a good year, right?
Oh, no, I don't think so. I think if that would mean that of all the students I had educated, there'd be 40 who were like me. I mean, that'd be pretty dangerous. That would create an overpopulation of physicists if every physics teacher generated more than one, successor.
So obviously, based on what Eric said, and I would have, when I was a high school teacher, I would have 2 before I switched to IEL, and a lot more those who wanted to be physics majors after. But that's not the point. The idea is that very few people will continue on doing physics professionally. So why do they need physics? Well, there are many reasons, right? To get a college credit, for example, to get a college credit if they are doing an AP course, or have physics on their transcript if they're going to the university. But these are not, the goals that are very, I would say, crucial for me. I would say that the goal that we can achieve with an introductory physics course is to help people learn to think like physicists, to think like scientists. Because while they are touching upon individual concepts once, or maybe twice, or maybe spend a few weeks on them, if they learn to think in a certain way, we can repeat this thinking process again and again and again for every concept. And this way, by the end, they will be so skilled in this process that they will be using it almost automatically. So my idea is to brainwash people into thinking like physicists. But you will say, what about the normative curriculum? They'll say, well, thinking like a physicist is not, you cannot do it, I would say, on an empty stomach. You need some content, right? About what to think like a physicist. And this is where the normative content comes in. We can think like a physicist about moving objects. We can think about interacting objects. We can think about objects that will rub with something, or that are magnetized, or whatever. So this is how the normative content comes into play. Now, it's not the facts and concepts and rules that determine your, that are the most important. The important is the process. So this is the content. The process becomes the content, and our normative content becomes the context. But what happens once you get used in this process, once you start thinking like a physicist, the process of mastering this context speeds up. And that's what we see with our students. At the beginning in September, everybody moves very slowly. It's very hard to, get people to design the experiments, to collect data, to analyze, to see uncertainties, to draw motion diagrams. But then they kind of speed up and move much faster. So that allows us to use more of a traditional curriculum content in our classes. But there's another aspect that is very, very important. Think about what our students learned in their lives. They learned to skateboard, they learned to bicycle, they learned to play computer games, they learned to operate their cell phones. Did we teach them that? We didn't. They learned by themselves. They are expert learners. So if we build learning of physics on their skills as a learner, and that involves perseverance, ability to fail and get up and do it again, collaboration with people, looking at good examples and learning from them, seeking feedback. They all know how to do it. That's what they do when they play computer games. That's what they do when they learn to do all kinds of tricks on skateboards or jumping off cliffs on bicycles. But what they didn't learn yet is how to read a scientific text. And that's why many teachers say, oh, I don't use the textbook because my students don't read it anyway. So that's the skill that we need to teach them. And in our system, we have a very efficient way how to learn to work with the physics textbook. It's called interrogation method, and I can talk more about it. But what I want to say, if we teach the students how to think like a physicist, and what do I mean by that? Asking yourself a question: are we dealing with an observation of a phenomenon? Are we dealing with a pattern? Are we dealing with a hypothesis? Are we dealing with a testing experiment? Where are we in the process? And they know how to work with a scientific text, and we have a good text for them to work. Then we don't need to do everything in class. Certain things they can learn by themselves, and we can help them working in groups, self-assess and assess their knowledge. So, as I said, three things that are important. First is that you focus on helping people learn to think like a physicist, not so much to memorize Newton's second law and Newton's third law, but use Newton's second law and third law to help them learn to think like physicists. And second, build on their strengths as learners and convince them that they have their strength. And we have a special activity how to do it. If you ask me, I'll tell you. It's called an expertise activity designed by Yu Fan Lin and David Brooks. And the third, teach them how to work with a scientific text as an expert. And I see a question, so is knowing it, it's knowing the process? It's not knowing the process. It is, how do you say, being habituated into the process. When you habitually come to the classroom and say, Eugenia, what are we doing today? Oh, we observed yesterday and found patterns, so today we're going to analyze them quantitatively. Or we came up with 3 different explanations yesterday, so today we're going to test them. So this habituation is this number 1 step, this idea. The second idea, as I said, building on students' strengths as learners. And the third, helping them work expertly with a scientific text.
Thank you. And I think really You know, it's putting the focus on the process, as you said. There was an interesting thread in the chat. I mean, you used the phrase "thinking like a physicist." I mean, we could easily generalize that to science as a whole, right? I mean, thinking like a scientist, or not.
Well, I would say that physics lends itself easier to this thinking, because in physics, the phenomena and systems are simple, and variables can be isolated. It's not like biology where systems are complex, and experiments take a short time. So if we have 3 different explanations and we want to test them, we can design an experiment, use these 3 explanations to make predictions what should happen in that one experiment. If this explanation is correct, if that explanation is correct, if the 3rd explanation is correct. I'm sure you do it in your work, right? And then run the experiment and compare the outcome to the prediction. So you can rule out some explanations right away, and some you need to test more and more. In biology,
but that's not quite true in all domains of physics, right? I mean, if you think about high energy physics or cosmology, there are no quick experiments.
Right. Absolutely. And that is and it takes sometimes 50 years. But what we teach in our courses is not what is happening now. And so our method allows you to kind of fake this time, right? To shorten this time. And we can do it for biology, but in most experiments in biology, if you want to run a testing experiment yourself, not in nuclear physics and gravitational waves, but in something simple. For example, where does mass of a tree come from, right? So there are different explanations that people have. It comes from the water, it comes from the soil, it comes from the air. So how could you test it, right? How can you test these 3 different explanations? So the experiment that was done historically took years and years, because you had to plant a tree and weigh the soil and water that were used for the tree to grow, and then find out that the mass of the water in the soil is nothing compared to the mass of the tree. So the material could not come from the soil or from the water. And so you rejected them, but it took years. So of course we can come up with, this fake historical experiments like we would do for nuclear physics 50 years from now, but it's much easier in physics. So the systems are simpler and experiments are on average faster. So that's why teaching to think like a physicist, I think it's easier. And yes.
So I'm happy to see some hands up already. There's also quite an active chat. That's great. I mean, Eugenia, don't worry too much about the chat. I will take from the chat whatever is interesting and forward it to the stage here. But I want to encourage everybody to raise their hand. The sooner you raise your hand, the earlier you'll be in the queue to ask a question. Drew, you've had your hand up for a while, so please unmute yourself.
Thanks.
And where did you go? I lost you. Oh, you lowered your hand. Now I have to find you. Okay, because I want to add you to the spotlight. So there we go. Okay.
Hi, thank you. Yeah, this is certainly a very interesting discussion, and I certainly the question's a little bit off topic from the current discussion, but I think it's very interesting. I was curious more just from a logistical side of the way that you did labs during the pandemic, like the sort of the pedagogy which you talked about in your talk sort of lends itself, or is almost in-person type of interactions sort of help facilitate a lot of this sort of interaction and collaboration and the argumentation potentially as well. So I'm just curious from a logistical side of things, and also I guess have a year out, like how did you handle doing this in the pandemic, and what were the sort of results from that?
Well, the results were mixed. So what we did, we spent last summer, after the pandemic started, recording the videos of experiments that students would normally do in the labs, and many more, when we realized that there will be a whole year online. And we created a supplement. So we have the materials that people use. It is our textbook. So here's the textbook, right? Exploring and Applying Physics. It comes with the active learning guide, where the activities and the labs are there. And they're also online on the Scientific Abilities website. And so this active learning guide had a few videos of experiments, but most experiments students did in class, in the labs, or in recitations, or in the classroom, in the high school classroom, if it's a high school class. And so what we did, we created the online active learning guide, where the experiments that students normally did were replaced with the videos. For example, we have one of the first labs is called Where Do Cars Meet? So you have two cars that move differently. Students need to figure out how they move and predict where they meet, if they either go one after the other or they come towards each other. It's an application experiment, right? So they cannot do this, right, when they're in different places and working online. So we created a video of a real phenomenon. It's a snail, a real snail on the pavement, and you need to figure out how it moves. So we have some tools in the video, and then you decide, and does it move at constant velocity? Does it move at constant acceleration? Or it moves somehow differently? So just analyzing this video with the tools that they have to figure out how to use, where to use the scale for the snail, and other things, creates this collaborative environment. And we also created the files for the labs, where we interjected the rubrics, scientific abilities rubrics. So the students working in groups online could work on the same video, or we had very simple experiments that everybody had equipment for. And many people, including Rutgers Professor Michael Gentili, his lab course has practicals when students come and need to design an experiment without any guidance at the end of some period of time. They are given materials that it's called Pose Your Own Question Lab. So he sends photos of the equipment, and they need to come up with an experiment, and this would be some observational experiment. Then from this, they would come up with the model and test it. And so using the equipment that is available, and nothing was available, of course, right? And they're all at home, and many of them are in different countries. So they had to work in groups to come up with an experiment that each of them can do in a group. They needed to collect data, make it quantitative with the uncertainty analysis. They needed to observe something, create a possible explanation, test it. Can you imagine this task? It's an impossible task. And so after 8 weeks of instruction, one of the groups, that's the report that I read and loved, they came up with an experiment of what affects how fast potatoes burn in the oven. So they figured out that it's not just the volume or the surface area, it's a certain ratio of those, and they tested it, and they had different ovens and the different potatoes, and they accounted for the uncertainties. So what I'm saying is that once you have a mindset, you can come up with activities for the students to experience the same. Will all students do it? No. Will some of them never participate in group work and not turn on their cameras and stuff? Of course they will. But with the right motivation and the right activities, you can engage them even online. And while online labs is not the best thing in the world, they can be done in the IELTS spirit. That's what I was trying to say. And then, of course, you have such tools as PhET simulations that you can structure as aisle labs. And one of the examples is the quantitative analysis of photoelectric effect, right? You can do all the observational and testing experiments using PET simulation.
Okay, thanks.
Did I answer your question?
Sort of, yeah. I guess I was more curious about like how the students are actually interacting with one another. Like, are they meeting synchronously, asynchronously? Are they meeting on like Zoom? Are you meeting as a class? Like that sort of.
Okay, different versions, but they usually work on a Google document, on a joint Google document. So the report comes as the result of a group, and we started doing it long before the pandemic started. And then it's either they meet and work during the lab time, or they meet outside of class, and then they come to the lab time and meet with the instructor and have a discussion. So there are different ways of doing it.
All right, thanks. I asked this because I'm writing my thesis literally right now as we speak on this.
Okay.
Thanks.
Thank you.
Thank you for that question, Drew. Maksuda Frost, you've had your hand up, so please unmute yourself. And
all right. Hi. So my question is a little bit different. It goes to assessment. In your talk, you talked about the idea of like grades are so important, and I agree with you. And especially if you're teaching upper level, like advanced physics, IB physics, they seem to care about their grades even more, right? The very first day I walked into class, I had the kids complain about me, like immediately to administration saying like, oh, she doesn't give us any answers, because I was like, I want you to design an experiment about motion. And that's all I told them, right? And they were like, what type of motion, what equipment do you want us to use? What are the rules? What is this? What is that? And the whole point is they should be trying to figure these out by themselves, right? How do you deal with the fact that assessments are still important, right? What type of assessments would that look like? And just if you're teaching upper level classes, like they literally, if it's a 90 instead of a 90, if it's a 91 instead of a 92, they will come back to me like, what can I do to fix that, right? How do you change that particular mindset? And what about the students who, as you said, at the high school level, they don't necessarily come in with this critical thinking piece, right? Or they just do those grades. So what are formative assessments or formal assessments would this look like in a one-year course with trying to teach all of the physics?
Yes, it's a good question. First, I wouldn't personally, while I would really enjoy doing your design experiment about motion, we give this experiment after a similar task after they had 5, 7, 10 weeks of designing experiments with our guidance. So we start with the guidance of what to think about. And you can see the examples of our experiments on the Scientific Abilities website that is in my talk. For example, as I said, you have 2 cars. You need to figure out how each of them moves at constant velocity or constant acceleration, and then set them 3 meters apart and predict the location where they will meet. It's still a design of the experiment, but it's much more scaffolded in terms of the goal. And so the goal of the experiment needs to be clear. And then we also divide experiments into 3 different types: observational experiments, testing experiments, and application experiments. And for each of the experiments, we have specific guiding questions that help students think what to think about, not what to do. For example, if it is an observational experiment and they're observing a phenomenon, we ask them, what kind of data can you collect about the phenomenon? How are you going to organize this data? How are you going to look for patterns? How are you going to explain the patterns, right? So these are not specific to any, they're not telling them what to do, they're telling them what to think. And then we're helping them to learn how to think this way. So I'm going to share my screen and to show you what I mean and what this grading means. So I'm going to share my screen for a second. So this is a rubric that the students have when they do their lab, for example, right? And we have 39 of those rubrics. And this is for just one ability that we want them to develop, that they are able to record and represent data in a meaningful way, right? So they have this rubric in their lab report, in their lab handout. So when they're collecting data, they see, okay, you know, I recorded all the data, but now how will the person navigate where these data are and how they're analyzed? So they go and they revise the organization of their data. And we have these rubrics for everything that we want them to do in a lab, for example. Then when they're doing the lab, they, I will not stop sharing just for a second because I want to show another example. They're looking at these rubrics and they self-improve while they're in the lab. And then I, as a teacher, use the same rubric, and I don't give them any feedback. I just say, okay, for this particular ability, record and represent data in a meaningful way, you get needs improvement. But for these two abilities, for example, you identified the uncertainties, but you didn't differentiate between random and experimental. Or you distinguish between experimental and random, so you get an adequate on this. And they have these rubrics, they're all published, they're free, you can use them. And they know exactly what we expect, right? So it's not about the grade, it's about what we want them to learn. So they submit the report, you give them the grade, and then you give them a week to improve. So if they improve it, which takes, it's all lab reports are, as I said, on Google Docs. You see the improvement right away. It takes you literally 30 seconds. And they say, oh, you moved from inadequate to inadequate. They're happy because it's about learning. You're happy because they learned. Here's an example of an exam question. Right? This is Sarah and Eric. So now think about this question and about Sarah's and Eric's idea. And you need to think about how you would convince Sarah or Eric that they're incorrect. And so what are we assessing? We're assessing, representing, evaluating, designing an experiment to test a hypothesis, because both Sarah and Eric express hypotheses, right? So changing the assessment to match your goals and giving students the tools before you assess them creates a completely different atmosphere. And that's what I talked about in my talk about, I'm going to, let me show you one more question while I'm talking. That's another question. It's an exam question, right? That allow them to develop this growth mindset. And eventually, if you have good questions and good feedback and allow them to improve, they stop caring about the grades so much and start caring about learning. It is your behavior that has very huge potential to change what they think about learning. So we have the tools, how to help them. And I think that your problems can be solved with the tools that we have.
All right, thank you. No, I really did like the experiments you did with the whole balloon and the rubber air. That was really, it was nice to scaffold it, right? Like, oh, is it the air? Is it the rubber?
Right.
And just keeping on adding complexities to it, right? I agree. All right, thank you so much.
You're welcome.
Thank you. And thank you, Maksuda, for bringing topic to assessment, which is something, as you may know, from my talks, is something that I've been hammering on relentlessly lately. Let's see. I saw another hand up, Michelle, but it went down. Oh, there. Hi, Michelle.
Oh, sorry. Now I'm unmuted. I had a similar question. I mean, it was about, mine was about student buy-in, and I think that's what Maxuda was asking. Like, again, if I don't use traditionally what students have expected, I get a lot of pushback from students and their parents that I'm not teaching them physics. So I just didn't know if anybody else has any experience on the buy-in. And I had asked some questions in Perusal, and you had answered one about the scientific ability rubrics. You had just showed us those. But how does that work with copying and not becoming overwhelmed with this regrading, or is it just like part of the plan of your class? Because when I hear about resubmission, I already feel kind of overwhelmed with the amount of grading that I do. So I don't know if you could speak to that and how maybe this process eases that up.
Right. I actually have a PhD student, Danielle Bouget, who is a high school physics teacher. She defended last year, and if you send me an email, I'll send you her dissertation. She has been doing all my teachers who I prepare do resubmissions. So, and I've done them. I've been doing them all my life, including my high school and middle school teaching times. So there you can see in more detail, how it's done. But so I think behind the resubmissions is the philosophy, right? So what do we want the students to think about learning? Is it a process or it's a stamp? So we come to a doctor and the doctor measures our blood pressure, right? And the blood pressure is a little high. And the doctor says, well, you need to, move more and you need to worry less. And then we come again and the doctor measures our blood pressure. I'm not very good with medical examples, but the doctor does not say, your blood pressure is high, too bad, stamp. That never happens, but we do it in our teaching, right? You cannot do it, too bad, we're moving on. So we come across, we collectively as educators, not as people who want our students to learn, but as people who want to stamp them with a diagnosis and walk away. And the students know it because when they come to you, they already have many, many years of experience of this stamping. So you are not fighting the students on this. You are fighting the experience because they very quickly figure out what the education is about. It's not about learning. It's about stamping them with a grade. And when we complain that they worry about the grade more than they worry about learning, it's not their problem, it's our problem. We created it. And then we blame the victim. Right? So if you think that your goal as a teacher is to help people learn, you start thinking what learning means. Learning is a slow, difficult process of struggling, winning and losing, and winning and losing again. That's what we do when we do physics, right? You write a grant, Eric, how many of your grants were funded without revisions on the first try?
Like not even 10%.
Right. So most of the grants come back, either they're not funded at all on the first try and you need to wait a year, or you need to revise a lot of stuff and invite more people or kick out some people or change your experiment or whatever. Your papers, I have over 100 published papers. One paper was published without revisions, one, right? So if I were a student, I would ended up with one published paper. You would never know about IELTS. So our educational system goes against learning. And when we are trying to ask ourselves why students don't want to learn, because we don't want them to learn. We want to stamp them, right? Okay, so now it feels like, oh, Eugenia is blaming the teachers. I'm not blaming the teachers, I'm blaming the system. So the question is, what if one teacher changes? Everybody else, that was my position when I started teaching in 1982 in Moscow, School 43. I was the only one for all 13 years of my teaching there who did resubmissions. How did I do it? At that time, no computers, no copying, nothing, you know, real experiments and the typewriter with 6 copies. I would come to school every day, 45 minutes earlier. The door of my classroom was open and it was full of people. And then, you know, somebody would come, Michelle is walking in and says, Eugenia, this is this quiz. I didn't draw a force diagram for this thing correctly. How can I fix it? I say, okay, here's the situation, go draw a force diagram. And then I say, Sarah, could you please look at Michelle's force diagram? Do you agree with it? If you disagree with it, can you help her? Because Sarah has the same problem. Now Sarah and Michelle are working together. So I would have 15, 20, 25 people in the morning working together, coming to me. I would quickly look at their work. I know their work by heart. So it takes me literally 3 seconds. I would ask one question, 5 seconds, and they will go and I will increase their grade. And then the next day they will come in the morning and say, you know, I woke up earlier. Do you need any help? So that was in the time of no Google Docs. So now it's a Google Doc. They submit the assignment to me and I can edit it in real time. If I have a moment, I say, oh, you know, Michelle, look, you got the answer, you forgot to evaluate it. And Michelle, oh, sorry, here's the evaluation. So you have this instant feedback. And somebody said that and I don't remember whether it was you or somebody else, my school does not allow resubmissions. And I responded, well, too bad, leave the school then. I'm kidding. But there was another person who said, well, don't call them quizzes or lab reports, call them drafts. Then there's you don't need to fight administration. That's actually the thing that I teach my students, is that, you know, you can have different rules for your administration. Some of them, they're very good, and some of them maybe are not so good. So you have your own heart and your own soul. You know what's right. Close the door and do it. And you're wise enough to know how to do it. So nobody knows. And I didn't tell you that.
I appreciate your feedback. Thanks.
And I did not hear anything, Eugenia. So we have another hand up. We have about 18 minutes left. So if you have a question that you'd like to ask, but you're not quite sure, make up your mind fast because we'll be running out of time. Joe, the floor is yours.
Thank you. Hi, Eugenia. It's wonderful to see you.
Hi,
So this is a question about using rubrics at different grade levels. And my question is, have you noticed that students' performance on the scientific abilities rubrics changes as they get older, as they get more practice with these abilities? So specifically, if we're using the rubrics in a vertically aligned department, what differences would we see in the rubrics in 9th grade versus 11th grade?
So we have different versions of the rubrics. You know, we have the POOM curriculum modules. So if you don't know about them, just Google POOM Rutgers EDU. Oh, no, POOM ilphysics.net. Sorry, PUM ilphysics.net. And there are different versions of the rubrics. And what we find in the schools that use the rubrics in, let's say, middle school teachers and high school teachers, that middle school teachers who come to the high school, you know, feel like they don't need them anymore, that they already know what to do. And we see it the same with our college students, algebra-based courses. By the end of this year, they say, we don't need the rubrics anymore. We know them by heart. So it's, as I said at the beginning, it's kind of a habituation into thinking in a certain way. And once you start thinking this way, then you kind of cannot think any other way. So if you look at a number that you measured and you understand that it's not a number, it's an interval, and you learn about it when you're in 9th grade, then of course in the 11th grade you will not write that your coefficient of friction is 0.3. You will write that it's 0.3 plus minus whatever it is. So I would say in the rare cases where our rubrics are used vertically, we see huge improvement. But I said in rare cases, okay, because there are very few school districts where we have teachers in middle school and high school using different versions of the same rubrics. But in my experience, a year is a good time for them to master. So even if you get the students who have never seen them, in 1 year, they get totally proficient. And I have now a high school teacher, Oren Levy, in Princeton. I don't know, you were not in his year, right? You don't know, Oren. So he switched to standards-based assessment, and he uses rubrics for all his assessments and tracks progress of his students. So he doesn't have any grades anymore. And I have many teachers like this. So if you're interested, I will connect them. I think they all, God, I don't remember when you were in the program, which year. Some of them are older program-wise, and some of them are later. I have 2 amazing women in Hackensack who are doing it. So I have many teachers I can connect you.
Thank you for that question, Joe. So I see there are no more hands up. We still have some time. So if you'd like to get a question in, please do so now. Maya, the floor is yours.
Hi, thank you. My name is Maya. I'm a teacher in New York at a public school here. And this is a very different way, I think, of teaching, of assessing than a lot of people are used to. I'm curious, is there a specific way that you begin the school year to kind of introduce this, the aisle method, or just this more, how do you do that?
Well, we have different activities. They're all published and free. So if you join the group, I'll put it in the chat. There is a, is it to all? Send the chat to everyone. Okay, it's called Exploring and Applying Physics. There we post stuff, and there are files for active learning guide online, which show the activities to use. And when it says online, the beginning of the year school year activities are the best there. So I'll tell you the activity, the very first one, to get them in, kind of not fear physics. So my husband is a photographer. He's a physics professor and everything, but he is a photographer, and he has a ton of cameras. So we placed the cameras in the house, and we took a video of somebody walking and taking the video of this 12 cameras, different cameras. And that's the video that students watch. And I tell them, this is my house, which is true. Tell me what you see. And we see, tons of cameras. What are you thinking? They will say, well, you must be a photographer. I said, what's the difference between I see many cameras and you must be a photographer? And they say, well, one is an observation and the other one is a guess, right? That's what a hypothesis is. I said, okay, so which question does it answer? And they say, why do you have these cameras? Okay, so we see that you have the cameras. Now we're asking you why, or how come you have them, right? So now we're developing an explanation. So I get them into groups, and my teachers get them into groups, and they come up, we call them crazy ideas, right? Why I would have these 12 cameras. So, and then they put them on the whiteboards and share. So I can be a thief, I can be a photographer, I can be a collector, I can be, a person who writes reviews, okay, so which one are you? And they ask me, and they will answer to them in some gibberish language or in the language that I know nobody knows in my class, like Slovenian, for example, right? And they're like, what? I said, well, you asked me, right? I answered, but you cannot interpret my answer. What does it mean? Oh, we did not anticipate that you will speak a different language. I said, that's exactly the nature of experimentation, of a testing experiment that you tried to do. You did not anticipate the answer, so you cannot interpret it. Oh, we need to design new experiments, they say. Okay, so they start thinking of how they can test whether I am a thief, right? So if I'm a thief, they should not find any receipts, right? But what does it mean finding receipts? It means you need to know what the receipts look like. So it's kind of a new experiment. You need to buy new equipment that detects receipts. Okay, they come to the house and they find receipts. Does it mean that I am not a thief? No, but if they find receipts, then I'm definitely not a thief, right? So rejecting a thief is very easy, but finding receipts tells me nothing about whether I'm a photographer or I'm a collector, right? So if I'm a photographer collector, the prediction is you'll find receipts. So this is not a good experiment to rule out a photographer or a collector. So what experiment would you run then? And we go through, and at the end, I say, so do you know why I have 12 cameras? They say, no. We know you're not this, you're not this, you're not that, but we don't know for sure what it is, right? We ruled out those, but we have not ruled out that you have 10 children and you are giving them gifts as cameras, right? So that was the last idea that they couldn't rule out because they, all experiments that they did would not rule out 10 children, for example. So this is the process that we will go through. And the thing is that many teachers would do some kind of a fun activity at the beginning of the school year and then continue lecturing. But after this activity, we proceed to the balloon activity, right? So now we do a physics thing. And now we analyze the steps that I showed you, observe, find patterns, come up with explanation. And then you start doing it for every idea that they construct. And it becomes a routine. So from the very silly thing, and 20 years ago, I didn't do cameras. I would say you walk into my house and you see 10 TVs. So what are you thinking? Why would Eugenia have 10 TVs? Okay, come up with with 3 crazy ideas. Why? And so one of my teachers, Richard Theckhorn, one year sent me an email, a story that he had a student, a female student, who was sent him an email at the end of the school year. Not her, but the father of that girl sent him an email, thanking him. This girl loved physics. They had physics lessons every day at dinner, and so he praised Richard. Long, and at the end, P.S. Would you please tell me why you have 10 TVs?
Thank you.
That's a wonderful anecdote. We have 7 minutes left and 2 hands up, so we'll need to handle both of those, and we need to leave a minute for me to make a final announcement. Alyssa.
Thanks. So Alyssa Levy, I teach physics in East Harlem, New York. Eugenia, I use your book for AP Physics 1. I teach 9th grade physics. Emily Pontius and Josh Ruppert got me excited about this stuff 4 years ago, and now I'm hooked. So my question is, I'm the only science teacher. I'm the only physics teacher in my school. The other science teachers are really excited by what they see, and they want to also get involved. You had mentioned the reasons why physics is a simpler entry point for IEL, but what would you suggest I tell the other sciences, right? The biology, the earth science, for how they can get their students thinking this way too?
You know what, Elisa, tell them that I will be happy to meet with them and talk to them. So they send me an email, we'll set up a Zoom meeting, and I will tell them how to start. It is a long process, but there are several key steps that that they need to start with. Okay, I just worked last year with people who teach philosophy at Lehigh, and they're teaching philosophy with an IEL approach now. And all it took them working together and me coming in like once every couple of weeks in the summer for an hour, reviewing what they did. And they said that in the first 2 weeks of a philosophy class online, their students wrote better philosophy papers than after a semester before learning in person. And the course was asynchronous. Okay.
That's incredible.
Yes. So it can be done, but people need to, so let them watch the video, let them watch this. And I also yeah, so tell them to email me and I'll tell them what to do. And we will get together. Okay.
Thank you.
I'll be happy to do it. And other people, if you have math or physics, biology teachers who are interested, maybe Elisa can organize more schools and we will get a meeting and talk about it.
Do it. Let's do it.
So be this community organizer.
Wonderful. That's you're creating a lot of work for yourself, Eugenia, but we're all very grateful for that.
Wow, that's my very special skill, you know.
Okay, final question of the day, Bill.
Hi, Eugenia. Bill Durkee. I teach freshmen and AP Physics 2 in San Diego at an independent school. And I had a question that was similar to Alyssa, but it also sparked a question about how you use the IEL approach when you're dealing with a prescripted curriculum like AP IB that has particular content goals for the end of the year.
Okay.
Maybe I'd like to learn about what teachers' experiences with this are, and you know, just what are successful approaches, and maybe there's resources that I can read about that you could point us to. But
well, as I said, if you're using our textbook, it is.
I'm going to be using that this year with the AP class. I just
right.
Yeah.
You started, right? So make sure that
I will be doing that this year.
Oh, you will be doing. Okay,
yes.
So join the Facebook group and pose your questions there and send me an email. I will connect you to one of the AP teachers who teaches AP 1 and 2 using the IEL approach and the textbook, and has amazing results. I have many, but he's the most successful.
Okay.
So so you're wondering about the coverage or uncoverage.
Yes.
Right. So he can share the exact steps of what he does.
Okay.
Okay.
Thank you. Yes, thank you very much.
So thank you, Bill, for the question. Thank you for joining us at this early hour from the West Coast. We're nearing the end here, but I can't stop myself from asking you a follow-up question to Bill, because in some sense, the AP assessment is philosophically diametrically opposite everything you stand for, Eugenia, in terms of being high stakes, leaving no room for failure, being completely content-based rather than process-oriented. And I know a lot about it because for close to 8 years, I tried to as a member of the AP development committee, to change the test. But the ETS is like this monster that, can only go into one direction, namely the one that they've always gone in for many, many years. So how do you reconcile that? I mean, the fact that, yes, you can teach it in a way that it stimulates curiosity, this intrinsic curiosity to learn, but then in some sense, the test itself kills it.
Well, as I see Marta posted a very good comment here, that the revised AP 1 and 2 are very process-based. They're not like old APB. So that's a help. Yes, I understand is a high stakes and but it is the end. It's like a driver's test. You pass or you don't pass. And if you don't get a good grade on AP, you just take a college test. So it's not a problem. But I think that the revised AP test is much more conducive to our methods. And actually in our textbook, we have a ton of problems. We learned to design new problems inspired by AP 1 and 2 over different kind of problems that enriched our problem base. Actually, if you do not have our textbook, get it for free from Pearson to just to look at the problems. And so this is a good thing. But as you approach this final test, right, you make a choice how your students learn to this test. And what I'm arguing that using the IEL approach is very good for doing well on the AP test, as well as on the MCAT, because they reward process thinking much, much more, especially AP experimentation, the questions on experiments, based on experiments that they have. If you don't know how to design experiments, you will never do well on those questions. So I completely agree that with Marta, that the revision of the test, I hope they don't go back to what they were a long time ago when you were fighting. I don't know when you were on that committee, but
I think it was like 15 years ago.
Yes, so about 12 years ago, they started the redesign. And it's very, very different. Yes, and I think it encourages what we're doing and supports.
Well, that's good to hear. So it's 12:01. So I really want to thank you, Eugenia. I think we could have gone.
Let me just, Frank, send me an email. I'll send you the PDF. I never sent it back.
So I want to thank you for stimulating this fabulous discussion. I think we could have gone on for another hour, and I want to thank all of you for participating so energetically. We're going to take a little break with these talks, presuming either late August or early September, so that everybody has a chance to recover from 15 months on Zoom. I also want to encourage all those of you who are new to these talks and have not joined the PoLS-T Network Slack workspace to click the link. You may have to scroll up a little bit, or maybe Sarah can put it in the chat again. That way you can asynchronously chat with other people. You can join a certain interest group. I mean, we can keep the conversation going. And finally, even though we're taking a break for July and August, we have one more exciting event coming up, which is the PoLS-T Exchange, which is a mostly asynchronous conference where all the talks, or nearly all the talks, are presented asynchronously, but still permit interactivity through perusal. The talks will go live on June 23rd, so that's 5 days from now. And the live sessions will be on June 29, June 30, and July 1st, between 1 and 4 p.m. Each day we'll have a keynote, and we have some really exciting keynotes lined up. And then we have an hour of discussion with the presenters of the talks that match the theme of the keynote. And then we have an hour of socializing on an innovative new platform that permit people to interact with each other. Sarah has put the link to the exchange in the chat. Be sure to register. The other thing is that one of the things I really want to accomplish this coming year is that we grow this network. I mean, one of the things that we heard loud and clear from many physics high school teachers that they felt rather isolated. Here is a way of connecting with each other, learning from each other, helping each other. And as I put in the chat a moment ago, changing the world for the better, because I think, the type of thinking skills you learn as a scientist are conducive to being a better citizen in society for everyone, not just for practicing scientists, but for all people. So thank you again, Eugenia. This was absolutely wonderful. Yeah.
I'm just trying to raise my hand many times.
Oh, sorry. I didn't
Yes,
mean to
I just,
ignore you.
Yeah, Eric, I wanted to thank you for inviting me, and I wanted to thank everybody for coming, and Eric for running this amazing community about which I did not know, and I will join the network, and I will encourage my teachers to join it too. So I just wanted to thank you all for first commenting on the video, reading my responses, coming here today, and Eric and Sarah and Callie, thank you very much for this organization. I'm just blown away by this. Thank you.
Well, wonderful. Thank you so much. A virtual applause. Thank you all. I hope to see you at the exchange, if not when we resume in September. Thank you. Be well.